Hello, everyone. Yeah, thanks for joining our webinar series of the Sphere Energy Battery Week. Today, we're going to talk about our automatic ECM and P2D model parametrization app and how we speed up the optimization and parametrization of these models drastically. Let me first go into the agenda for this talk today. We're going to do a little introduction on our company, Sphere Energy, and ourselves. We're going to show why it's important in these days to model batteries, and also why there are still some pain points when parametrizing these batteries, and why we have developed our application. Then we show what we actually do to accelerate the parametrization and optimization process with our app, and how AI can support in doing that. Then we're going to have a live demo of the app and a Q&A session afterwards. So first, let's talk about Sphere Energy. We are an engineering solutions company focusing on building and engineering solutions for physical product development. We have our battery technology center in Augsburg, where we test batteries and collect the data. We have our Zurich AI Competence Center, where we build AI solutions. Here, me and Kais right now, we're sitting in the Munich office, our beautiful new Munich office, the data science lab. And we have the engineering hub in Paris, where we focus on building hardware solutions. And there's three important pillars to our work. First, we do advanced data management, we do artificial intelligence solutions, and we do smart data generation, as we're going to show today. A little introduction about us. My name is Lorenz Planck. My background is in applied physics. My master thesis was actually about P2D modeling, so not too far away from the topic today. And at my work at Sphere, I'm focusing on building AI solutions along the product development cycle.
Yes. Hello, everyone. I'm Kais. I also have a background in applied physics, with specialization in energy harvesting and storage. At Sphere, I assist with everything battery modeling, ECM and P2D, and I also help with building our tools and the frameworks that we use internally.
So yeah, let's go right into it. So the first point is, why do we model batteries? The first important point here is we want to reduce DOE matrices in testing. Testing is expensive and usually takes a long time. So accurately calibrated battery models, either ECM or P2D, can help reducing these test efforts by basically filling in the blanks in between these tests. So you don't have to test all of the conditions that you want, but can simulate some of them by calibrating the model on the measurement data that you have. Then they're also important for BMS applications. So the battery management systems, for example, applied in cars. There you want to have accurate state of charge and state of health estimations, and battery models are an essential part in making these estimations accurate. Then battery models can also help in understanding battery behavior and thereby facilitating better optimization of cell design. And the last important use case, one that we actually use a lot, is battery models can help to get more intelligence to AI models. So AI models we use for lifetime prediction or end-of-life prediction of battery cells. And we found that adding parameters, adding more intelligence to these AI models based on calibrated models on real-world and synthetic data helps to increase the accuracy of these models by a lot. This is now a use case that shows how DOE matrices can be reduced with battery models. On the left side, we see our DOE matrix, or design of experiment matrix. We have a temperature. We have different temperature conditions on the left side. and different discharge rates on the x-axis. And the purple points are basically the ones that were tested. And the blue fields here in this matrix are the ones that were simulated. And here on the right side, we see the plots of discharge curves, so voltage over time, for one of these slices of this test matrix at 20 degrees. So the markers that we see here are the measurement data that were collected during testing, and the dotted lines are the simulation results. So the model was calibrated on these measurement marks, and then we have predictions for different discharge rates, which are these dotted lines. And we could show that we can actually reach super high accuracies on these types of tests. So now what is the problem? What are the pain points in battery model optimization and parametrization? The first thing is usually the software that is needed to calibrate these models is quite expensive, and it's usually part of a larger modeling framework. So you basically even if you only want to model batteries, you basically have to buy a larger product having unnecessary costs attached to it. Then setting up these models is a lot of manual work. So you have to know what parameters do I want to optimize. You have to set up your experiments. You have to choose the correct bounds to get well-calibrated models. Yeah. The next point is usually modeling batteries has a very high entry barrier. So the first thing is you have to have a lot of knowledge and experience in battery modeling to use the software, and the software itself usually requires a lot of tutorials, and it's just not easy to use right away. And the last point is computation time. P2D models especially require a lot of computational power. And especially when you run, for example, aging simulations over many cycles, and then you optimize these models. So you have to run them multiple times to get the right parameters. This can take a lot of time. So this is also a limiting factor. So we have 4 pillars to tackle these problems. The first one, we built a very user-friendly and intuitive GUI. So it's only focused on battery modeling. You have already set up tests where everything is set for you. So using it has a very low entry barrier and is quite intuitive. The second point is we have AI support in setting up the models. So I will go into more details on that a little bit later. And also the pre-processing of the data is supported by our AI. Then we have an efficient streamlining of the parametrizations. So all of the data that is generated and all of the parameters that are optimized, everything is set up in a nice and intuitive, streamlined way. So you don't have to worry about your data management. Basically, everything is handled by the tool. The last point, and a very important one, is we are collaborating with Stackit. It's a Germany-based cloud infrastructure. So you can run a lot of parametrizations and simulations in parallel. This speeds up the process by a lot, because even for one optimization, you can run hundreds of simulations at the same time, speeding it up drastically. Now I'm gonna show how our AI helps in setting up the simulation. So what we did is we created over 10 million digital twin P2D models and ran beginning of life tests, aging simulations for calendaric and cycling simulations at varying protocols with RPTs, without RPTs, and basically trained our model to give a rough estimate of what kind of parameters this type of data would map onto. So what happens in the app is if you upload your data and you say what kind of test you want to optimize for, the model already gives you the right bounds. So you don't have to think about, okay, in which order of magnitude could this parameter be? You don't have to do this additional research. This is all efficiently handled by the app. And to show you how this looks. We've prepared the demo, and Kais is now gonna jump into it and show you how this looks.
Yes, thank you very much, Lawrence. So let's start with the demo. Let's go on our platform first and log in. Right. So when you first log in Apex Physics, this is the first dashboard page that you'll land into. And I will take this opportunity to kind of introduce you a bit to the Apex Physics app. So as Lawrence described it pretty well, the Apex Physics app is a tool to help you create models for a battery based on your characterizing measurements that you might have done in the lab. That includes ECM models, P2D models, and also includes aging, if you have like cycling measurements or calendaric aging measurements. Exactly, and Apex Physics helps you in three major ways, I would say. First, it assists you with setting up the optimization by giving you the smart recommendations, as Lawrence just said. It's also an automated way to proceed with optimization. You have the option of restarting optimizations automatically by changing bounds, depending on some threshold that you set, like an RMSE between measurement and simulated results from the setup model. And also the third axis is that it allows you to tap into our computational power and therefore deploy more or less resources depending on the optimization you are running. Exactly. So in this demo, I will run you through one BOL optimization of a P2D model. And afterwards, we will use this model for a short simulation as well. And as I do that, we will look into the GUI together and we can go through the different elements as we proceed. So first, let's set up a new cell optimization. And this is the optimization screen. You can see different things you can set up. Maybe most importantly for now is this main card in which you define your cell properties that you already know. So that's things like nominal capacity, some safety features like the voltage bounds, but also if you happen to have done some teardown tests or to have extra information on yourself from literature or from things that you tested yourself, you can add that knowledge here and basically attribute a value to that parameter that you have measured and then not optimize for it, therefore gaining time by adding this insight. Let me load in an ongoing project so we don't have to fill all the fields during the demo. But this is an ongoing project that already pre-set up. It's for the LG E78 cell. This is made with open source measurements. And here we can see already like the battery chemistry changed. Here it's NMC graphite, which is correct for this cell. I can input the nominal capacity, for example, here. And we can see that it appears in our known parameters now. And if we scroll a little bit down, we are introduced to kind of how we structured an optimization in Apex Physics. So basically the way one optimization process looks like, it's broken down in what we call stages. And one stage is one instance of fitting parameters that are all described by the same type of measurement. So to explain that a little bit more, here I already have a stage set up. It's called OCV. So I will just like do OCV measurement here as I already preset it up. If I scroll a little bit down, that's where I can add measurements. So I can drag and drop my measurement, for example, but here we will load it normally. And then I can see my OCV measurement here appear in this table. I can check out the columns. I can see the columns were detected also automatically in this case for this OCV. And then I get an error here, and Apex Physics warns me that I need optimization bounds, which makes sense. This is the whole point of optimizing. So since we are doing an OCV, maybe things that we could parameterize for are geometric properties such as the electrode width. So let's add that in the optimization bound card. We get some recommendations already. We see the bounds are already like pre-filled by Apex Physics. So we can just add that optimization bound. Let's also add the initial concentration in positive electrode here directly, and we can see we also get directly recommendations. But let's say there is one parameter that you want to test an optimization for and you don't get it recommended. So here we can use our search bar and we can add, for example, the maximum concentration in positive electrode. So this is for an OCV measurement in this BOL parameterization that we're doing. And we have also AIS measurements for this LG cell, again, from the open source data. So one can add another stage, add one measurement here to define the stage in this pop-up. And then let's go ahead and add it. And then we can see our measurement appears. And here we can choose optimization bounds for this stage. So those are different optimization bounds because you get different information from AIS and from OCV. So here we will parameterize for contact resistance. Again, we get like some recommended value, as well as for negative electrode conductivity. All right. So here in this optimization card, one can choose the speed of the optimization, so how much resources you want to allocate. You might want to change this depending on the stage you are running. So for example, if we have a cycling stage where typically it would take a little bit longer, you would allocate more resources, whereas you would want to save them maybe from an OCV or AIS. So let's leave it there for now. And for this AIS measurements, I actually have two measurements from two different specimens of the cell. So we can add that as well. And then it will optimize for both cells. So exactly click on add measurement. And then here you can proceed with renaming this measurement so that we know later in the results. And we can choose the data for the second cell. Exactly. So now we have set up our optimization. I hope everything was clear. Otherwise, please don't hesitate to ask questions in the Q&A. And let's click on run optimization. And here we get prompted if we want to do an auto advance of stages or not. So auto advance means that Apex Physics will go from stage 1 to stage 2 and take decisions on if it should repeat a stage or not based on things that you would set up in the optimization setup. So for example, a certain RMSE, a distance from the bounds or such. But for now, we're going to run it without that auto advance. And when we press 1, we land in the optimization evolution page. And here we can see live how the optimization progresses, how the cost evolves with regards to iterations. Exactly. And now that the optimization is done, we get a user prompt. So this is the user prompt between stage 1 and stage 2. This user prompt has multiple important things to look at, mainly the parameters table. So if we look here, we can see a summary of our input bounds and the optimized value. We can also here have, for validation, a plot of the measured versus simulated OCV results here using these optimized parameters. We get also a summary of this optimization. So cost, number of evaluation, if it ran to completion, or maybe it converged early and such. But maybe also a very, very important feature is the recommended new bounds feature. So it's Apex physics, basically looking at the bounds, looking at the cost, and saying, hey, maybe if you try these bounds, you can get better values. So for this example, let's say I'm not satisfied with this fit. So I can look here at what Apex physics suggests. I can also change these values, for example, before rerunning, if I know better than Apex physics. And then I can do a retry stage, for example. And we're back at the optimization view, and we can see already like our cost is lower than in the previous try. And of course, like the accuracy increases as you increase the number of retries or the number of iterations during one optimization. But let's say now I'm satisfied with the results of this optimization, and let's continue to the second stage, which was the AIA stage with the two cells. And here the optimization is running. Okay, it's started. And we can see it already evolve and improve slightly. Of course, like how fast you converge and the accuracy of your results will depend on the computational power you allocate for the different stages, but also how your bounds are. Okay, it looks like it already converged. It's almost done. Okay. And here in the evaluation, we get like the two evaluation plots for the two cells. So this is cell 1 and this is cell 2. And just as before, we get recommended values to retry, or we can, here, let's say we're satisfied with this parametrization, we can download the parameter file and quit. And the parameter file can then be used in third-party software that can support P2D models, which is what we set up right now. Exactly. So now we're back in the cell models dashboard, and we can look at our optimization that we just run. So when we click on view details in our optimization, we get this drawer that comes out with a summary of the final costs, the final parameters. We can also do the optimization from here if we're not satisfied. We get the different validations for the different cells, but we can also go to a more detailed page where we also have more visualization options for the validation, such as body plot or real and imaginary things for the AIS measurement. What we can also do from the dashboard is just take the model directly to our simulation page and run simulations directly there. So here you can see I clicked on take to simulation, and I'm taken to the simulation page with the model already preloaded here. I can give my simulation a name, demo, for example, and here we can define different measurements that happen one after the other. let's say I want to try something, but there is no pre-made options for it. I can go to the custom measurement here, and then I can prompt Apex Physics to basically make me a simulation scenario. I can validate it, and then I can just run the simulation. So to try that out, we can just go ahead, type in prompt. I want to run an RPT protocol, for example, with pseudo OCV at C20 and capacity tests at different series. Let's click generate and see what happens. All right. So here we see that Apex Physics generated a recommendation of a profile. So current profile that I can look at and validate, and a temperature profile. Here we didn't specify temperature, so it's 25 degrees C. And we can see here, we can recognize the C20, hopefully. This is 79.9 divided by 20. And these seem to be the different C rate capacity tests. If I'm satisfied with this, I can just press run simulation. Otherwise, I can reprompt and revalidate basically before running. So let's just run this one. Okay, it's finished. And now we are in the simulation results page. And you can see here a summary of your model. You can summon the drawer from here and do everything you could from the dashboard for this particular cell. You get simulation summary with the prompt you used, the model you used, as well as different plotting options. So here by default, it's time versus current. And you can add a plot of time versus voltage if you want, depending on your needs. If it's like cycling simulation, you can plot the RPT versus how much SOH is left in the cell. So yes, you can simulate quite some things. And after that, you can export the simulation results if you want to validate this then. So yeah, I think that was it for the demo part. I'll be giving it back to Lawrence now. Continue.
All right. Yeah, I mean, that was our demo. That was our introduction into our Apex Physics app. We will also offer a free trial of the app starting July 2026. If you're interested and you like what you saw and you want to try it out for yourselves, yeah, we will offer this free trial. And if you're interested, you can just contact me. You can see my email here, lorenz@sphere-energy.eu. And yeah, we're very happy for everyone that's interested to try it. So just feel free to reach out. And I think with this, we can move on to the Q&A session. I see there's already a lot of questions here.
Yes.
So let me open them. All right, so we have a first question that is, hi, thanks for the demo about the EIS measurements that you added. Are they full cell or half cell measurements?
So those were full cell measurements. They were even like measured in system. So those measurements were conducted of the cells while they were plugged into a car. So these measurements are really particular in that, but we can see that it also works well.
Okay, then we have some great technical questions here. Are your EIS P2D simulations in the time domain and post-processed or directly in the frequency domain? The latter is drastically faster. Maybe I can answer on that. So we've actually implemented both solutions. We have a brute force method, let's say, where we actually apply the sinusoidal current to the cell and then do a post-processing step. Yeah, this can help when you try to combine different models, and it doesn't always work in the linearized way, but we also have the direct frequency domain option for faster convergence and faster simulation. So then here we have the approach here seemed very much leaning on physical models. Is the advisor role of the AI that suggests the optimized parameter bounds, model options, and model option optimization settings the only thing that the AI does at the start, but then the simulations run purely physical?
So maybe I can answer this one. So yes, the role of the AI is the assistance role. You can see it. We also have like AI functionalities in like prompting the simulation as well. So what runs in the background depends on the model we have. So right now we support P2D and ECM models, but eventually, so right now what we demonstrated was, yes, purely physical, but eventually we will also have pin-based models, and then it will be different here.
And just to make it clear, we have our AI-based simulation. This is only for the prediction of the aging behavior of cells. Our colleague Gianmarco is going to talk about this in the talk tomorrow. It is important to distinguish between the two. This is our setup to calibrate physical models as efficient as possible, but we see that physical models don't perform so well in making aging predictions for battery cells. This is where the AI really exceeds, and this is what we're going to talk about tomorrow. This, what we've shown today, is about physical models and how to get to those parameters most efficiently.
Yes.
Okay, yeah, a lot of questions. Very nice to see. Do you do sensitivity analysis to determine the parameters that have to be optimized, or is it only based on the AI model you develop? Yeah, this is currently only on the experience of the AI model. We have not done any extensive sensitivity analysis. But there is an intrinsic sensitivity analysis in the AI model because we trained it on a lot of different parameter combinations. So the model has learned intrinsically what the sensitivity of these certain parameters will be for the different tests. Okay, then we have what kind of optimization algorithm do you use? How do you make sure that you get a global minimum? We actually have multiple options available in the tool. The two we have implemented right now is differential evolution on the one side, so a genetic type of algorithm, and Bayesian optimization are the current two options. And yeah, as with every optimization, you never can be 100% sure that you have the global minimum. In order to reduce the likelihood of landing in a local minimum, you need to increase the number of iterations and the population sizes that you run. Then, how long does it take to run a cycling aging calibration in your setup? So this heavily depends on how much computation you throw at the optimization algorithm. I would say one cycling simulation takes about, let's say, if you run 1,000 cycles, it takes about 1 minute to run. But then you're limited by how many you run in parallel and how many generations of optimizations you have. But from our experience working with it a lot, usually to get an accurate result, even for complex aging behavior, it takes about 2 to 3 hours. Yeah, if you want to take the next.
So during the optimization stage, are several model types supported, or is every P2D model an SPM? That's a very good question. No, you can also do DFN models. So for example, in the optimization I just showed for the OCV, it was like an SPM model, and for the AIS, it was a DFN model. Also, like Apex Physics, like activates the right submodels for you depending on the measurement type you put in. And we also have support for ECM models. So yes, so you can have multiple models in Apex Physics. It's not only SPM.
I think the next question. So you asked the AI if it can create RPT with C/20 capacity test. Why did it create the dynamic currents? I think this was part of the prompt, right? Because you said
Yes,
that-
I asked for like a C20 OCV, which we got, and then capacity tests at different C rates. So that's you just like maintain one current and see how much capacity you get out before reaching your voltage bounds in charge and discharge direction, and that's what we got. Exactly. And also like those were basically made after each other. So it was first OCV, then the C rate capacity tests in one single profile. So maybe that's what you mean by dynamic. Yes.
Okay, the next question is also a very valid one. How can I validate that the model I calibrated actually works for other use cases?
So here, of course, if you have measurements that you've done on the lab, so for example, like some drive profile measurement, like from a car, or measurements that you do in the lab, you can export the simulation results from Apex Physics and then validate. There will also be like plotting functions in Apex Physics which allow you to import like measurements and like plot things on top of each other that would also allow you to validate. Exactly. So let's continue.
Yeah, the next question, is Apex Physics useful only for lithium ion or fundamentally different battery technologies like aqueous zinc batteries? At the moment, we're only focusing on lithium ion batteries. We're planning to also include solid state batteries, but currently it's mostly focused on standard chemistries used in lithium ion technology.
Yes, and we have multiple chemistries implemented. So we have NMC, we have compound models as well. So some involving silicon in the anode, and yeah, but just lithium ion for now. Okay, so a question from Samar. What parameters does your physics-based model optimize apart from electrochemical ones? Can you also optimize thermal, mechanical, and aging parameters with the tool? Yes, you can, and you can also parameterize an ECM model. So that would be basically optimizing for resistances and capacitances instead of like the electrochemical parameters. And to optimize for aging parameters, you would need some sort of cycling data or current aging information, but yes, you can.
On the mechanical side, this is a very interesting topic. This is not currently supported to simulate things like swelling behavior. We have plans to integrate that, but for now, for the first version, for sure, this will not be there. But all the other things you mentioned, thermal, aging, will be available for sure.
Another exciting question. Is it possible to export your model in form of FMU for usage in other tools? For now, we support the export of the model parameters, but yes, FMU support for co-simulation is also like planned. So then you can just like export the model as a complete FMU and use it in Daimola or Simulink eventually if you want. So I hope that answers your question as well.
Okay, let me think. Let me see if we missed some questions.
I don't think so.
How does electrode width function in a P2D model? Normally, it should be a dimension that is neglected. I think you're talking probably about electrode width. And in the case of a P2D model, even if it is basically a 1D simulation, you can extrapolate the results of the simulation to the different dimensions and thereby get then an accurate model of the battery. So the width, for example, scales directly with the capacity of the cell. If you imagine like an unrolled jelly roll, the wider it is, the more capacity the cell will have at the same thickness. And thereby it's actually a very important parameter in getting in the end to a correct digital twin or model of the battery.
Yes.
All right. I think that was a lot of great questions. We have one more question. That is, what is the benchmark for your 10 times faster battery modeling? This is mostly based on our own experience. We've been using the app extensively ourselves, and we parameterize a lot of models that we also test in our test center to feed this data to our AI model. And we see with setting up these cells and automatically running the bounds adjustments that we get to well-calibrated models a lot quicker than we did before. When we used, for example, a purely PyBAM driven approach like PyBob, or also from personal experience with other software tools.
Yes. So yeah, the overall improvement in efficiency of like the workflow like comes from like this assistance from Apex Physics, but also to the computational access as well, because like you can then deploy the resources you need and you get a better or faster optimization than you would have on your local machine as well. All right. I think that was it for the questions.
Okay, then thanks everyone for joining the session. And yeah, we hope we're going to be hearing from you, and have a great rest of your day.